In this video, we're going to go through Unit 3, Block 1, Example 1. We're going to use the first derivative test to identify the local maximum and local minimum points of this given cubic function. So we have a third degree polynomial given to us, and we're asked to find local max and min. To do this, we're going to follow our first derivative test steps. Number 1, we're going to find the first derivative. Number 2, we're going to identify any critical points of the function f of x. That is, we're going to find where f prime is undefined and where f prime is 0. Number 3, we're going to use the first derivative test. We're going to draw a number line on the entire domain of f of x. We're going to put any critical points on that number line, and then we're going to test f prime on each interval in between and each interval on either side in order to identify if f prime is positive or negative, thereby telling us if f is increasing or decreasing. This will help us identify our conclusions about local minimum and local maximum points on f. When you guys are doing this procedure, you can use Excel to help you with some of the solving, and definitely you can use Excel to help you with the testing. But what I insist on is you need to be showing your work, showing your conclusions, and interpreting and writing out exactly what's going on and why you're coming to those conclusions. So I'm going to do a few examples here. Your work in your written homework and on your exams should closely mirror the sort of work that I'm showing here. So one nice way to lay out your work is to have two columns, where on one side you have your mathematical facts, and on the other side, you have your interpretations and conclusions based on those mathematical facts. Your mathematical facts may come from you showing symbolic work and solving equations by hand, or it is okay for you to also use Excel for a lot of the solving that we do in this class. But if you are going to use Excel, then your mathematical facts over here would reference your Excel file and then you would attach it. So first step, mathematical fact. Step number 1, we need to find f prime of x. So I'm definitely going to write down on my paper the derivative. So going back to our f of x function that was given, I'm going to find the derivative. That'd be 6x squared minus 24x plus 18. Step 2, we're going to find critical points of f, i.e. we're going to find where f prime is undefined and where f prime is 0. I want to first note f and f prime both have a domain of all real numbers. That tells me that there are no critical points of the variety where f prime is undefined. So I'm just going to note f prime is never undefined. There's no x values that you could plug into this derivative function and get an undefined value out. You're not going to have any problems with dividing by 0 or square roots of negatives or anything like that. So that's not an issue in this problem. So now I do need to find where f prime of x is 0. That's going to tell us places on f where f is flat. F is flat when f prime is 0. So I need to solve where the derivative equals 0. This is a quadratic function, therefore it could equal 0 at 2 places or 1 place or 0 places. So you can use Excel to identify where the quadratic equals 0. Just make sure you're clearly trying to find all solutions. Or this is a nice easy quadratic, so we certainly could solve it by hand. I'm going to go ahead and approach this both ways. If you solve by hand, you could factor and solve. If you factored this, you would find that it's 6 times x minus 3 times x minus 1. And so one solution is x equals 3. One solution is x equals 1. Okay, so that's one way to solve by hand. Another way to solve by hand would be to use the quadratic formula. Remember, that's x equals negative b plus or minus square root of b squared minus 4ac all over 2a. That is x equals 24 plus or minus square root of 24 squared minus 4 times 6 times 18 all over 12. So x equals 24 plus or minus square root of 144 over 12. And that would give you x equals 3 and x equals 1. Same answers, just doing it using a different method. And lastly, we could use Excel to do this. But either way, I get a solution of x equals 3 or x equals 1. Now, it is extremely important that you go off to the side here and you make some conclusions about what we just discovered. So I'm just going to note what I'm trying to make conclusions about here is the behavior of f of x. Ultimately, I want to identify local max and min on f of x. So again, I'm just going to note f has a domain of all real numbers. That tells me that the graph of f of x exists everywhere from left to right. There's no holes, there's no jumps, there's no breaks. It just smoothly exists left to right. It's continuous and exists everywhere. I have now discovered f prime of x equals 0 only at x equals 3 and x equals 1. Its derivative is a second degree polynomial. The derivative f prime only has two solutions, two places where the f prime is 0. That means f of x is flat only at x equals 3 and x equals 1. So by showing that f prime is 0 only at those two places, we have shown that f is flat only at those two places. Now recall, that does not mean, it does not guarantee that f has a local max or a local min at those points. Remember, f could look like this. That's a place where f is flat. It could look like this. That's a place where f is flat. So those would be max and min. But it's also the case that f could look like this. It comes up, flattens, but then keeps on increasing. That's not a max or a min. Or it could come down and flatten and then keep on decreasing. So we know f is flat at x equals 3 and x equals 1, but we still need to understand which one of these shapes does it have at each of those critical points. All right, so that's where the testing comes into play. So step 3 is testing. We're using the first derivative test to find local max and min. That tells me we're going to draw a line. We're going to put our critical points in order on that real number line. So this real number line extends left to right with arrows on the end to indicate that the domain of f exists everywhere left to right. I now put x equals 1 on the number line, and to the right, x equals 3. Those are my two critical points. I'm now going to start merging the mathematical facts side of this page with the conclusion side of this page. I'm going to actually on the number line, always write conclusions about what's going on with f prime and also what's going on with f. So first I'll start with the critical points. What we've learned is that x equals 1 causes f prime to equal 0. At x equals 1, the derivative is 0. And my conclusion about f would be at x equals 1, f is flat. So I've made a little conclusion about what's going on right at x equals 1. Similarly, at x equals 3, f prime is 0. So f is flat. So I made a little conclusion about what's going on at x equals 3. These are the only two places where f prime is 0. That means f prime must be entirely positive to the left of x equals 1, or f prime must be entirely negative to the left of x equals 1. I know that because it couldn't be positive and then become negative because it would have to pass through the x-axis. It would have to become f prime equals 0 to change from positive to negative. But it doesn't do that because the only places f prime is 0 is at x equals 1 and x equals 3. So f prime is either trapped, being positive over here, or being negative over here. Same thing in between. F prime is either entirely positive or entirely negative in between these critical points, and f prime is either entirely positive or entirely negative to the right of x equals 3. So all I need to do is plug in some x value to the left of x equals 1. It doesn't matter what x value. Pick any x value to the left of x equals 1. I try to pick one that's easy to work with, like x equals 0. And you plug it into f prime. F prime of 0. We're going to plug in x equals 0 to the derivative and see, is the derivative positive or is the derivative negative? And then I'm going to plug in an x value here in between x equals 1 and x equals 3. For example, x equals 2. Plug it into the derivative and we're going to see, is the derivative positive or is the derivative negative? And lastly, over here, I'm going to plug in an x value to the right of x equals 3. Again, it doesn't matter what x value, just pick one that's easy to work with, like x equals 4. We're going to find f prime of 4 to see is the derivative positive or negative. At this time, I'm going to go ahead and open up Excel so we can quickly and easily evaluate and see what's going on with this derivative function. In Excel, I have picked some x values ranging from negative 10 up to positive 10. In column B, I put the f of x values. In column C, I put the f prime values. Notice here at x equals 1, f prime is 0. Also, at x equals 3, f prime is 0. And now notice x values below x equals 1, f prime is positive. Then, right at x equals 1, f prime is 0. Then, right in between x equals 1 and x equals 3, f prime is negative. And then, to the right of x equals 3, so higher than x equals 3, we see again f prime is positive. Okay, so coming back to my work over here, showing my work and my reasoning and my conclusion. For x less than 1, we see f prime is positive. It's not just at x equals 0 that f prime is positive. It's for any x value down here. You can see that in this table. All these values for x below 1, the derivative is positive. Then, at x equals 1, the derivative is 0. Then, at the interval from x equals 1 to x equals 3, in particular at f prime of 2, we get negative 6. On that entire interval for 1 up to 3, we see f prime is negative. You can pick any x value in that interval and evaluate f prime. You will get a negative value. And lastly, we looked at the interval after x equals 3. And at the interval after x equals 3, we again see f prime is positive. So in particular, f prime of 4 is 18. So we can say for x is greater than 3, for all of those x's, f prime is positive. Since f prime is positive on the interval for x less than 1, we can say f is increasing. Remember, f prime positive means f is increasing. Then f is flat, and then from x equals 1 to x equals 3, f prime's negative, so f is decreasing. Then f is flat again. Then for the interval for x greater than 3, f is increasing again because the derivative is positive. Right now, I actually have a complete description of f. It's increasing, then flat, then decreasing, then flat, then increasing. So it must look like this. Increasing, then flat at x equals 1, then decreasing, then flat at x equals 3, then increasing. So f of x seems to look like this. It's got a local max at x equals 1 because the derivative changed from positive to negative at x equals 1. It's got a local min at x equals 3 because the derivative changed from negative to positive at x equals 3. In Excel, in my little text boxes, I could write all these conclusions. So for x less than 1, we have f prime is positive, so f is increasing for x below 1. For the interval 1 to 3, we see f prime is negative, so f is decreasing on the interval from 1 to 3. And for x greater than 3, we see f prime is positive, so f is increasing for x is greater than 3. And lastly then, I could make a conclusion here about the local max and min. F prime is 0 at x equals 1, and f prime changes sign from positive to negative. So f has a local max at x equals 1. And lastly, we can make the conclusion about the local min here at x equals 3. F prime is 0 at x equals 3, and f prime changes sign from being negative to being positive right at x equals 3. So that must be a local min. Last but not least, we can now describe it. I also sketched a little graph of it over here. I'm going to insert a little graph there. And you can see it goes up, comes down, and back up again, just like we thought. Max at 1, min at 3.